Hey guys, welcome back to my channel. How's it going? Today we're diving into some fundamental concepts of probability theory, experiments reliability, and how we measure chance itself. In our previous video, we discussed the events, the sample space, and the basic axioms of the probability theory itself. But today we're going deeper and we'll explore how mathematics think about the uncertainty and why combining probabilities isn't as straightforward as it might seem. So let's start with something we see all around us: uncertainty. Whenever we deal with random experiments, there is always this question hanging over us: will something happen or not? And that's where the probability comes in. It's our way of measuring the chance, of putting a number on our uncertainty. First, let's understand what we mean by the experiment. In our first video of this course in probability, we mentioned that experiment, it's any process that produces an outcome under a fixed set of conditions. Let's call these conditions by number of epsilon. Think of these conditions as the rules of our game that stay constant each time we run the experiment. So it is important for these conditions to stay and remain the same, because if they are not the same, then the probability of our event will be very low. So let's say we have the conditions epsilon, which fixed and stay the same when we run our experiment every time. This is the first condition for our probability experiment. The second condition for our probability experiment is that we have some kind of sample space. The sample space is a set of all possible events. It can be interpreted as a set of sets or the set of elementary events. Elementary event is the event which consists of one possible outcome. Let's denote this event as E1, which is the set, actually. And let's say we have some kind of set which contains these sets. Let's say we have the sample space, which is sometimes denoted as E or S, which equals to the set of sets E1, E2, E3, and so on until the En. This is the sample space. Sample space where Ei, Ej is just elementary event, which equals to the outcome of this event. And let's say we have some kind of sigma. Sigma is a system or set of all possible subsets of the S. So sigma is all possible subsets of S of the sample space. It could be S itself, it could be the empty set, and it can be E1, it can be the set of consisting E1 and E2, or E1, E2, E3, and so on. There are lots of subsets. For any sets of this system and of this set, there are three operations defined, and which is possible. The first one is sum and difference of the two sets, so we can say that S minus empty set equals to the S itself. The product of two sets are also defined. That's why we call this a field or set of subsets. But this is just formality. You don't have to bother about this too much, because it's just a formal definition of what the sample set is, and we already discussed the probability of the sample space equals 1. And we also said the probability of the empty space equals 0. The brilliant thing about the probability is how we can capture it with just number between 0 and 1. If we are absolutely certain something will happen, we say its probability is 1, or sometimes we also refer to it as 100%. So in this case, the sample space occurs with a probability equals to 1. It means that no matter which outcome we have, in any case it will be sample space. No matter for every I which belongs to the set from 1 until the n, it will be obvious that set S has occurred. That event S, or sample space, has taken a place. Has taken a place means occurred. If conditions epsilon is realized. That's it, if our conditions of the experiment do not change. If we are sure that event will not happen, we say that its probability is 0. We can say the probability E prime equals to 0, which means its probability equals to 0 and this event will not happen. Now let me give you a concrete example. Imagine we have a probability of 1 over 4. This means there is a 25% chance it will happen, and naturally 75% that it will not happen. Another way of thinking about this in terms of odds, we'd say the odds against it happening is 75 to 25%, or simply 3 to 1. It is pretty easy, because everything that lies between 0 and 1 is our set of probabilities. That said, for every possible elementary event of our sample space, we have the corresponding number. There is a corresponding number, which is called Pj, which equals P of Ej, which equals the actual probability of this event. This is called the probability. Now let's talk about the empty space and the zero probability, because it is a very interesting topic. Suppose we have the probability of the event equals 0, like this one. But what is particularly interesting here is that even if we have the probability of this event equals to 0, it doesn't mean the event itself is an empty space. So we can definitely say that if our event is an empty space, that said, our probability of this event equals 0, because this event is simply not possible in the context of our experiment. For example, if we're tossing a coin twice, we cannot say that it will come up 3 times with a head, because this event is simply not possible in the context of our sample space. That said, its probability equals to 0. But what is particularly interesting here is that if the probability of our event equals to 0, it does not mean the event is an empty space. It can be a non-empty happened event. So even if the probability of this event equals to 0, this event can still occur. And how does this happen in practice? Well, let's suppose we have a segment of numbers from 0 until the 1, and let's try to choose the number from this segment. For example, it is a number x which belongs to this segment. Now let's try to choose this number. What's the probability of choosing the number, real number, let's say it is a real number, from this segment? Obviously, the probability of this event is 0. You know why? Just because we have infinite amount of elements between 0 and 1. We have infinite amount of numbers, because we have infinite non-discrete space. And this is really interesting, because some event actually happened and some number actually occurred. Some number definitely has to be chosen. Even if we say that for an arbitrary number x, the probability is 0, some of these numbers has eventually chosen. For example, if we say that the probability of the number 0001 is 0 and the probability of for the number 0020 and so on until the 1 itself, right? But we can say that as the result of our experiment, at least one number is chosen, one number xj is chosen, even if its probability equals to 0. And this is a really fascinating thing about the probabilities theory. Now, there are 2 main approaches and 2 main ways we can estimate the probability. The first one is what we call the classical approach. Here we count the number of ways an event can happen, and let's call this m. The m should be greater than or equal to 0. It should be non-negative. And we also have the total number of possible outcomes, which is n. And it is also given that this experiment is conducted under the same set of conditions. The same set of conditions, epsilon, is realized. Now we can say that the probability of an event, suppose the event Ej, equals the m divided by n, where m is the number of ways an event E can happen, while the n is the total number of possible outcomes. Let's make this concrete with a simple example. Flipping a coin. There are 2 possible outcomes. It is either heads or tails, and heads can only happen in one possible way. So our probability is 1/2, assuming that we are dealing with a fair coin, because these probabilities have to be equal. Since our coin is fair enough and our conditions as always remaining the same, in this case the probability of the flipping the coin and getting heads will be equal to 1/2. This is pretty easy. The second approach is the frequency approach or empirical approach. Instead of theoretical calculations, we actually do the experiment our own way many times. If we flip a coin 1000 times and might get heads 532 times, we would say the probability of this event is 532 over 1000 times. In practical sense, we'll get 532 over 1000 times. The more experiments we conduct under the same conditions, the closer our frequency probability will be to the theoretical classical probability. That's that our p of h prime will approach to its corresponding classical probability, which equals m/n, which is really fascinating. And here where it gets really interesting when we start talking about the predictions. If you have one reliable statement about an experiment, That's pretty straightforward. If you have two reliable statements together, it is usually fine, though you might be a bit less certain about both happening together. And when you start dealing with many reliable statements at once, something fascinating happens. The reliability doesn't just stack nicely. It is like trying to balance more and more plates and sticks. Each plate might be stable individually, but having them all stay up becomes increasingly unlikely. For example, if you have a chance of some event happening, for example, the chance of this event equals to E1, suppose, equals to 98% or 0.98, and if you have the chance, the probability of the second event in the similar range like 0.99, if you have this third one which equals to 0.95 and so on. If you have, for example, 100 of these events, like 0.97 as well, very unlikely that all these events happen simultaneously with the same probability. That said, it is very likely that one of these events will not happen, and reliability of the statement will increasingly fall. Both our approaches to probability have their own drawbacks. With the frequency approach, how many trials is enough to get the viable results? These questions led mathematicians to develop something more rigorous, an axiomatic approach. In understanding these basics, what an experiment is, how we can measure the probability, and how reliability works when it combines the events is crucial for diving deeper into probability theory. And in our next video, we'll explore this axiomatic approach that mathematicians developed to address these fundamental challenges. Thank you for watching this video, and I hope you found this video helpful. If you have any questions, feel free to leave them in the comment section below. We also have our Discord channel. You'll find the link in the description, and you can also connect with me in LinkedIn to discuss mathematical challenges or any other topics. So see you in the next episode. Take care.